Hi guys, so today we are starting chapter 4, which begins our applications of derivatives. Even though we kind of did a small application already when we did the rates of change in 3.11, we're formally going to be using applications of derivatives in this entire chapter. So starting off, we are going to be looking at linear approximations. So linear approximation uses the derivative, which, remind me, what is the visual for the derivative? How do we visualize that? I'm sure you just said that out loud to yourself. The slope of the tangent line. So we're going to be using the slope of the tangent line to estimate the change in f without actually calculating that change in f. We could just do that by taking the function, calculating the output at one point, calculating the output at another, subtracting them, but we're going to use the tangent line to approximate that change instead. Now, because the linear approximation is using the derivative or the slope of the tangent line, the linear approximation is also referred to as the tangent line approximation. There we go. So I have two graphs here because not only are we going to be using the tangent line to approximate the change in the outputs, we are also going to be using it to approximate outputs themselves. So in this first visual, I want to talk about that aspect of it. So right here, that is my actual f of a plus delta x, which I should probably explain that really quick. A, we're taking the tangent line at A, and we're going to go a small distance x away, and that would make our next coordinate a plus delta x. So right here, this is the value that our tangent line is approximating f of a plus delta x to be. So if we were to plug a plus delta x into that tangent line equation, that would be the output that we would be approximating f of a plus delta x to be. So I'm going to say that that is linear approximation. Or the tangent line approximation. Of f of a plus delta x. And then on the other hand, we can use the tangent line to estimate the change in the y values. So here's our actual change in outputs, that distance. So the output later on minus the output earlier on. What the tangent line is approximating that change to be is output for the tangent line later on minus the output of our point from earlier on. So as you notice, these are not great approximations. These are pretty far off. That is because the tangent line approximation or the linear approximation should only be used for small changes in x. If we were to have had a smaller change, like let's say that small, that coordinate would have been pretty close to the actual coordinate. That change in y values would have been much more accurate. So the further out you get, the less accurate these approximations are. The closer you stick to that a value, the easier, or the more accurate. So I want to go through the process of actually estimating those values. So if I want to estimate the output at a certain point using my linear approximation, or if I want to use that tangent line, we actually need to know the equation of the tangent line. Remember, that's y minus f of a equals f prime of a times x minus a. And remember, we're approximating that output or approximating that y value. So I'm going to solve for y by moving that f of a to the other side. We get y equals f prime of a times x minus a plus f of a. Now, if we're using this tangent line to estimate a value later on, technically this is not going to be exactly equal to the actual value of the function. It should be close, but it's not going to be exactly equal. So what we're going to do is we're going to use a different variable. I'm not going to say y, I'm going to say L of x, because we're technically calling this a linearization. We are linearizing, we're using that tangent line to approximate a value. So we're going to say L of x is approximately equal to f prime of a times x minus a plus f of a. And I would like you to go ahead and box this on your notes. This is a special formula that I would like to make sure that you know. So L of x is going to be the approximate y value that we're hoping to get close to what it actually is. Okay, so then we are going to plug a plus delta x. So that's the y value that, or that's the x value that we want to plug in to approximate the y value for. So we're going to plug that into L of x. All right, and then the next thing that we use this linearization for, or linear approximation for, is to estimate the change in those outputs. Let's go back up. Remember right here, I said that this is the approximation for our change in y values. I'm going to show the change in x values really quick. So change in x and change in y. That's slope, isn't it? Change of y over change in x. Specifically, what am I looking at the slope of when I draw that on this line? That's the change in y over the change in x for the tangent line. And that tangent line is drawn at A. The slope of the tangent line is f prime of A. So if we solve for delta y, that'll be a decent estimate for delta f. Okay, so we will estimate delta f using f prime of a times delta x. Box that as well. All right, last thing, what do we need to do in order to write a suitable linearization? By the way, when I say linearization, that means you're writing that L of x formula or that L of x equation. So what do you need to write that? Well, you're going to need to know the original function. And then you're going to need to identify the a value. Now the a value, sometimes you're going to have to choose that. And the way that you want to choose an a value is, it depends on two things. One, if you are coming up with that function, that a value should be a nice number that goes into the function that you can compute without a calculator. Sometimes that means also coming out like a nice whole number. It should just be a nice number that you can plug in that you get a nice output for. So you might want to write that down. And then the second thing that could depend on is if we're working with word problems and you don't actually have the means to find that original function, you just know specific points of information. The way that you choose that a value is, where do you actually know the entire coordinate for? Because when we're drawing that linearization, we better know the coordinate that we're writing the tangent line for. So if you have two pieces of information, that A value is going to be the X value that you have a Y value associated with, that you know. Not the one that we're approximating. That would be the A plus delta X. So let's go ahead and flip it over to the next page and try some problems. All right, so first thing that you want to ask yourself when you're doing these problems is, am I being asked for a change in outputs, or am I being asked for the value at a point? So change in F, or F of A plus delta X. I'll give you a second. Got it? So we are looking for a change in outputs. And the reason I know that is because I see subtraction, which tells me that I'm looking for the difference or the change in numbers. Now, what do I need for that? I'm going to need, let me write some stuff over here. This is where I'll do my final work. I'll need to know F prime of A and delta X, which also means I need to know F of A because I do not know the derivative yet. I need to know the original function in order to take the derivative. So it looks like, remember, I'm looking to approximate the change in these values, which means that this is the, hold on. This is basically the output of those two different inputs. So I need to know what was being plugged in and what was the function that I was plugging things into. Looking at that, it looks like there was nothing plugged in the numerator. It looks like it literally is just 1 over something. So I'm gonna guess the function is 1 over X. So if it's 1 over X, that means that I was plugging in 10.2 and I was plugging in 10. Now, which one of those would be my A value? Which one would that make more sense to be the A value? Well, which one's the nicer number that you think that we could probably take for granted that we know the output for? Do you know the decimal version of 1 over 10.2, or do you know the decimal version of 1 over 10? Because I know the decimal version of 1 over 10. It's 0.1. I'm going to assume that A was intended to be 10. All right. One thing I will do so that I can actually take the derivative of this, so that I can find F prime of A later, is I'm going to rewrite F of X as X to the -1. And then I'll take the derivative of that. And by the way, anytime that you need to pause this video and do the work on your own before you listen to me do that, you have the freedom to pause. All right, so derivative -1, X to the -2. And I'm going to try to do as many of these calculations by hand. So I'm personally going to rewrite that as -1, X to the +2. Remember, the part with the negative power is the only thing that moves. -1 is not being raised to the -2. It's just the X that was. All right, let's calculate F prime of 10. So that's -1 over 10 squared, or -1 over 100. All right, we have enough information to go ahead and calculate our change in Y values. Okay, so F prime of 10, that's -1 over 100. Delta X, remember, we were looking at the change for those X values that we plugged in, that was 10.2 and 10. So I'm going to look for the change in those. (10.2 minus 10, that is 0.2, or 2/10. Which would reduce to 1/5. So that is -1 over 500. Now, if you want to use the calculator, that is perfectly fine. I would just like to practice my mental math skills right now, and my written math skills before moving to that calculator. Just because, I mean, I guess there's a few reasons, but one of the biggest reasons is that on that AP exam, you're expected to be able to do a large variety of math problems without a calculator, like adding and subtracting fractions, being able to do some plugging in values into polynomials that are going to require at least some 2-digit stuff. So it'd be a good idea to sprinkle that in throughout the school year. Now I want to see how good my estimate is. So I'm going to plug in the -1 over 500 amount to see the decimal version. And then I'm going to plug in the actual original problem. Oops, I accidentally put a double negative. Okay, so I'm actually pretty close. Technically, because of the negative, my estimate is a little smaller than the actual change in the Y values. But if it was positive, my estimate would have been bigger. All right, now let's go ahead and use our linear approximation to estimate that actual output. So remember, to estimate that, we write our linearization function, that L of X function, which we have all of the information for. We need f prime of a, or I guess in this case 10, x minus a, or x minus 10, plus f of 10. So f prime of 10, that was -1 over 100. X minus 10, and then f of x was 1 over x, so f of 10 would be 1 over 10. All right, let's go ahead and use our linearization to estimate 1 over 10.2. That's a little high. Let me move this down just a line. Um, 10.2 minus 10 is just the 0.2. Okay. Oh, that should be the approximately equal. I remember calculating that amount before. That was the -1 over 500. Plus, to get a common denominator, I would multiply the 1/10 by 50 over 50. And I'm getting 49 over 500. Again, if you do that in the calculator, you can get a decimal amount, and that's perfectly fine. 0.098. Let's see how accurate that was. We are what? 1, 2, 3, 4, 5. We are accurate to the 4th decimal place. That is awesome. So technically our estimate is just slightly below the actual value, 1 over 10.2. All right, next problem. Estimate radical 9 using a suitable linearization, then actually calculate radical 9 on your calculator and determine whether the estimate is too large or too small. All right, so linearization, that means that you're writing your L of X formula. So remember, that means that we need to know the original function, f of x, and we need to identify our a, that nice value that we can plug in. So when I look at that cubic root of 9, I'm assuming that the function that I'm going to be using here would be the cubic root, and that I'm plugging the 9 in. Which I'm going to have to take the derivative of at some point. So I'm going to write that as x to the 1/3. And what would be a good a value? What's a good number that's close to 9? Because remember, I don't want that change in x values to be big. that would actually still get plugged into the cubic root nicely. You thinking the same number that I am? 8? Yeah, 8. And you don't need to write a reason up every single time that you do this, but because these are your notes and you might want to know later on why in the world did I choose 8 later on, I'm going to write a reason now. So I'm going to say because 8 is close to 9 and 8 goes into the function nicely. Or it doesn't go into the function nicely, but it's, f of beta is evaluated nicely. Okay. So for my linearization, we know f of x, we know a. We will need f prime of a. So let's go ahead and figure out what f prime of x is for now. So it's 1/3 x to the negative 2/3. I could go ahead and rewrite that as 1 over x to the positive 2/3. Oh, I'm sorry. 1 over 3x to the positive 2/3. Or I could rewrite that in root form and the thirds would become the radicand, or no, the index. And then that would become an x squared. Go ahead and evaluate f prime of 8. And remember, pause this whenever you need to. Okay, it's going to be easier to take the cubic root of 8. Keep your numbers small before you make them bigger. So that would be 1 over 3 times 2 squared. 2 squared is 4. 3 times 4 is 12. And then we'll need to know f of 8 for our linearization as well. Okay, I'm going to go ahead and write my linearization off to the side. F prime of 8, that was 1/12. X minus 8 plus 2. All right, let's go ahead and estimate L of 9. Okay, so that gets me 1/12 times 1, which is just 1/12. Plus 2 would be 24 over 12, or 25 over 12. Decimal version of that, 2.08333333. Okay, so let's compare our estimate to the actual cubic root of 9. I'll just write that as 9 to the 1/3 because I don't feel like going into the math menu. All right, so I'm going to take this to the same number of decimal places that I have on my paper, so 3. So our estimate is technically bigger than the actual value. All right, one more problem. A thin metal cable has length L equals 12 centimeters when the temperature is 21 degrees Celsius. Estimate the change in length when T rises to 24 degrees Celsius, assuming that DL dt equals KL, where K equals 1.7 times 10 to the negative 5th per degree Celsius. What is this? Or, oh, and K is the coefficient of thermal expansion. So what is this question asking us for? Are we looking for the change in outputs, or are we looking for the output at a specific point? There's a keyword in there, or I guess like a key phrase. Change in length tells me that I'm looking for the change in outputs, which, as a reminder, means that we are going to be doing, look at the front if you need to remember, f prime of a times delta x. So let's go ahead and label the rest of the information in here. I know dLdt is the Leibniz notation for derivative. So this is my f prime of x technically. That's my derivative. What's my a value? Do you guys remember when I talked about the visual here? And we can figure out our a value by looking for the piece of information where we actually know an entire coordinate for. Whereas if I was just given a single x value later on, I'm being asked to approximate that y value. So the a value has both pieces of information written somewhere in the problem, and then the one that we're estimating for doesn't. So if I'm reading this problem, I'm seeing that the temperature 21 degrees Celsius goes together with that 12 centimeters. That tells me that that's going to be my a value, and that one of those other numbers is my f of a. Now, which one's a? Is it length or is it temperature? Which one's the independent variable, like x is? There's two ways I can tell. Well, temperature usually controls everything. But I can also tell by looking at the derivative notation. In the denominator, it says dt, which would be referring to that independent variable. So this is my a, and that makes this my f of a. So what in the world is this 24 degrees Celsius? So estimate the change in length when T rises to 24 degrees Celsius. So that's that X value later on. That is my A plus delta X. Okay, let's go ahead and calculate the rest of our final pieces of information so we can be done with this set of notes. All right, I'm going to need to know the derivative at A, which was 21 that we said. My derivative function is KL. K, it says, is that thermal expansion coefficient of 1.7 times 10 to the negative fifth. And the L, well, we're going to have to use the L at 21, which we said was 12. So 2.04 times 10 to the negative fourth. And our delta X, well, I could take my A plus delta X and then subtract A. So that would be my 24 degrees Celsius minus my 21, which gives me a difference of 3. Okay, so 6.12 times 10 to the negative fourth. And then my label, remember this is measuring the change in F or the change in my outputs. In this problem, the outputs are lengths, and lengths are being measured in centimeters. So if there's anything that you should take away from this set of notes, it's these few things. One, when it says to write a suitable linearization or to use a linearization, you're writing that L of X formula, basically the tangent line, but you've added the F of A to the other side. When you see word problems like this, first thing you should do, figure out if you're looking for the change in outputs or the outputs at a specific point. So delta F or F of A plus delta X. And then label any information that you have. That way it's much easier to actually start the problem once you have all that information identified. So great job. Do you have any questions? Let me know.